In this presentation, I'm going to be going through the basics of using soil improvements, specifically building the soil organic matter and improving the tilth for water conservation. I'm going to start by just going through some definitions on soil tilth and the role of organic matter in soil tilth, and to describe for you how healthy soils will trap and hold soil moisture, and then give some options for adding and retaining soil organics and building tilth in the central interior of BC. Tilth is a very old word. Its original meaning being land that is suitable to cultivate. In the modern context, it's the physical condition of soil in relation to its suitability for growing a crop, and it applies equally to cropland, pastures, or rangeland. Good tilth is important because it contributes to optimal crop production. Soils with good tilth have good plant soil contact. It's firm enough for good direct root soil contact so they can extract nutrients from the soil, but loose enough to allow those roots to grow and forage out into new areas. Good tilth soils have good water movement and retention. The pore size space between the soil particles is large enough to allow water to enter and move through the soil, but it's small enough to hold on to any surplus that's there for later use. And they have good stable air spaces, so this allows the exchange of gases in the root zone, and it aids in soil warming. When we think about tilth, it's a very complicated biogeochemical process that goes on in the soils. And so what we do is we look at indicators that would be showing us what soils have that positive tilth factors relative to those that are poor. On the geological or the physical end, we look at the soil particle size, how they're structured, and the overall density of the soil. And on the biological end of indicators, organic matter is an important factor, as are root networks and the abundance of soil organisms. Starting with soil particle size, the primary particles of soil can be grouped based on size. The largest being sand, which range from about 0.05 up to 2 millimeters in diameter, so about the size of a grain of salt. Down to silt particles. To the naked eye, a silt particle would look like a pencil dot on a piece of paper. To clay particles, which are microscopic, not visible to the naked eye. And the relative proportions of sand, silt, and clay give us our soil texture. So this soil triangle developed by the USDA allows you to take your percentage clay, silt, and sand, and where those three lines intersect indicates what your soil texture is. Particle size is important because of the ability of various particles to aggregate. So clays easily aggregate to form structures by strong chemical bonding on their surface. So if you were to look at a clay particle under a microscope, they look like little plates. And when the surface of two of those plates come into contact, charges on the surface of the clay particle allow those particles to bind together. Now this aggregation, this chemical bonding, only occurs with clay particles. It doesn't occur in silts or sands. Silts, clays, and clay aggregates can also be bound into more complex structures with organic glues. And these form soil granules, which are also sometimes referred to as soil crumbs. But they have a range of particles and particle aggregates with large, small, and intermediate pores between those aggregates. Because of the various sizes and orientation of soil particles, they form different soil structures. Some of these are positive for crop growth, some of them are challenging for crop growth. Soils with a very high content of clay will typically form into either massive or platy structures. That means that all those soil clay particles bound tightly together form one massive block, or they form into plates with spaces between the plates. These do not allow water movement in abundance to pass through those structures. As you increase the content of silts and sands in with that clay, you can form either prismatic structures or blocky structures. So these are superior to either massive or platy in that they have large spaces between the soil aggregates, but within those aggregates the pore space is still very small. So overall it's an improvement in structure for plant growth, but it's not ideal. At the opposite end of the spectrum, sandy soils form what we would call a single grain structure. So here you get very high pass-through rates of water. There's large space between large particles, but they don't form into aggregates. So you're missing those small medium-sized pores that would retain water in there. The ideal, and what we're working towards in building tilth, is a granular structure. Here you got a variety of pore space. It allows good water penetration and good water retention. So structure is strongly affected by pore space, and that in turn affects the movement of air and water through your soil. So large aggregates have a pore structure. The spaces within them are too small and the spaces between them are too large. If you've got no aggregates, that's also problematic because the soil matrix is too easily disturbed. So if you think of a sand pile, it shifts and moves. It doesn't retain any stable pore space. Medium to small aggregates is best overall for plant growth. So just like Goldilocks found that middle ground between the too hot and the too cold porridge, it's that middle ground of aggregation that provides the best medium for plant growth. The density, or how tightly packed your soil is, also a very important indicator of tilth. Ideally, you want to have equal parts solid and pore space in your soils. And pore space decreases directly with increasing density, or the level of compaction, and this leaves less space for roots, air, and water movement. So even when you're doing something noble like moving organics out onto the field for enhancing your production, if you time that wrong relative to the soil moisture, you can compact, press the soil together, and some of that compaction becomes very difficult to reverse, particularly when you have a high clay component, because you will actually fuse those clay particles together through the chemical bonding on their surface. Organic matter plays a pivotal role in tilth as a direct and indirect vector for improving soil structure. So when you add organics, they decompose, and that decomposition releases sugars and other nutrients that feed soil organisms. So it's providing a substrate for other variables, as we'll see in a minute, that are very important for building tilth. That decomposition also releases polymers and complex carbohydrates, such as starches, that act like glue that puts the soil particles into good aggregates. So if you take a little bit of wet cornstarch or flour between your fingers, you'll note that it's a little bit sticky. And that stickiness, that glue property, provides a weak bonding which performs those good granular structures. Also, as a result of organic matter decomposition, you get organic acids that are released into the soil, and those acids can directly break the chemical bonds that bind the clay particles tightly together. So you're reversing those bad aggregations of the clays, and you're creating good aggregations between clays and all other particles. Roots are also an indicator of tilth, and having a good root network does many things that are beneficial to tilth. First is that they contribute a lot of organic matter to the soil. So plants have coarse roots and fine roots, which are sometimes referred to as root hairs. The root hairs are the foraging hairs, the ones that are out seeking nutrient pockets and water throughout the soil. And many plants will have a very large turnover in that root hair population on an annual basis. Sometimes 100% of the root hairs of the plant on a perennial plant will grow and then be shed and decompose on an annual basis. Root expansion can break apart large aggregates in the soil. And so particularly with large plants like trees and shrubs, you create a lot of hydrostatic pressure in the roots as they expand in size, and that will break apart very tightly bound soil aggregates together. And indeed, if they get into a fissure in a rock, there's enough pressure there to crack rocks. And finally, root cavities create pathways in the soil for soil organisms to move. So again, it's working on another tilth variable to improve the access and movement of soil organisms and the beneficial effects they have on tilth. And organisms do play an overall very important role in building and maintaining your soil structure. So they decompose organic matter into humus, or that soil organic matter, and organic acids. So they're releasing those beneficial chemicals into the soil. Or microbes deposit organic residues, which also act to aggregate soil particles. And then larger organisms, insects, worms, small mammals, will tunnel and burrow through the soil, creating cavities and mixing the soil.